Number 15. Helicopter blades withstand tremendous stresses. In addition to supporting the weight of a helicopter, they are spun at rapid rates and experience large centripetal accelerations, especially at the tip. Calculate the magnitude of the centripetal acceleration at the tip of a 4-meter long helicopter blade that rotates 300 revolutions per minute. All right, so here's our little picture over here. Here's the length of a single blade right here. And notice when this blade rotates, it creates a circular path, right? And the blade's radius the blade's distance is the radius of that path. All right, so the blade's distance is the same as the radius path. Okay, and it also tells us that it rotates with a value of 300 revolutions per minute. We know that that is an angular velocity, but the only problem is the units here are not units that we like to use, right? In our equations, they have to be radians per second. So first step is, let me just do a basic conversion here. 300 revolutions per minute, all right? Simply, revolutions have to cancel, right? So they're gonna go, let me make that a little neater. The revolutions have to cancel, so they're in the denominator. Radians on the top, because I know that there are 2 pi radians for every 1 revolution. Revolutions go bye-bye. I got to cancel minutes. They originate in the denominator, therefore their value has to go in the numerator. I'm going to put seconds in the bottom, in the denominator, that is, because I know the relationship between minutes and seconds, 60 seconds in a minute, so that cancels that, and I'm left with radians per second. All right, let's just calculate. So 300 times 2 times pi divided by 60, you get a value of 31.4, right? 31.4, and that is radians per second. Now we are good to go because this angular velocity now has the correct physical units in terms of using our equations and stuff. All right. So now, finally, so let's get down to the question. It says calculate the magnitude of the centripetal acceleration. So let's look for a formula that has centripetal acceleration. I do have 2 here on the right that I'm going to box in, but only one of them I'm going to use. Right, if we're thinking ahead, they gave me the radius and stuff, so most likely I'm going to be using this formula, right, that deals with the radius. So centripetal acceleration will equal the tangential velocity. Sometimes it's labeled v sub t squared. I think in your book it's just v, all right, squared divided by radius. So can we calculate this? Well, no, not exactly, because they didn't give us the tangential velocity, right? They gave us the angular velocity, and that's what this value is. So now I need to figure out, well, how can I relate tangential velocity to then angular velocity? And we have a lovely equation right over here, right, where it says that the tangential velocity, right, is equal to the radius times the angular velocity, right? So what I can do is I can take this piece and simply plug it in for my tangential velocity. So that will give me now, let's see, it'll be centripetal acceleration is equal to radius times the angular velocity squared, all right, all over r. Now I'll simplify this, r squared, basically distributing the square to the numerator. I realize that now, right, one of these will cancel with the denominator, r. So I have centripetal acceleration being equal to r omega squared. All right, so I'll put a little box around this because now I can finally solve, right? That's the formula I need. So let me do the calculation over here on the left-hand side. So say centripetal acceleration is equal to 4 meters, right? That's the radius times the angular velocity in radians per second. So that's 31.4, and that we got to square that. So simply just plug it into the calculator now. So 4 times 31.4 squared, easy peasy. So it works out to be 3,940. Okay, I've got 3 sig figs here. And that is in meters per second squared. Okay, that is the centripetal acceleration. That is the answer for letter A. All right, let's take a look at letter B. Compare the linear speed, aka the tangential velocity of the tip with the speed of sound. So now what we need to do, realize that the variable v here, right, I spoke about that before, is the tangential velocity. So now I'm looking on the right-hand side and I realize that I can use this formula right here because I do know all those variables. So I can solve for the tangential velocity, right? So we have the linear velocity or the tangential velocity being equal to the radius multiplied by the angular velocity. So all we need to simply do is plug in, right? Times now 31.4 Notice that this formula looks strikingly similar to this formula. The only difference is that my angular velocity is not squared. Okay, so now the linear velocity is just 4 times 31.4. So 126 actually, considering rounding and sig figs. So 126 meters per second. All right, and then it says compare that to the speed of sound, 340. I mean, it's less than. I guess that's a comparison. I mean, you could also do a ratio of 126 over 340, and you can see what fraction it is of the speed of sound. You know, something like that. All right, guys, thanks for tuning in. Please remember to subscribe, and I look forward to helping you with the next question. Take care.